Hey guys, so previously we discussed the concept of a limit and also we derived the definition for a derivative. So in this class we are going to extend on that, we're going to build up on that further. But before going into the advanced part, let's just recap what we did in our last class. We basically had a function, like this. The shape wasn't like this, but it would have the same concept. So our function was basically called f of x, and this function had a point. Let's say, let me give just some arbitrary axis. So this point would be x, and from this point there is a distance h. So this new point would be x plus h, right? And hence we can write that this point is x plus h comma f of x plus h, and this point is basically x comma f of x. Now why is that? Because see, for example, if you have an equation, for example, f of x equals to x squared plus 2, you could simply say that f of 2 is equals to 6, right? So you could write the coordinate as 2 comma 6, or you could have also written as 2 comma f of 2, because 6 and f of 2 are equivalent. So instead of writing 6, you could have written f of 2. So here we did the same thing. We wrote f of x plus h. Alright. Now what we did was we considered that what would happen if h becomes approximately equals to 0. So my idea was that when I take h and I try to approach this try to approach x is equals to 0, what happens to the gradient of the green line? You can see gradient of this line PQ. That is my important part to understand. So if we decreased h, for example, instead of h being this green line over here, instead of h being this, what would happen if we decreased h to, let's say, this distance? So the point would shift from here to here, and the point would come over here. So this green line would now become something like this, right? And the idea is that when you decrease h more and more, when you decrease h and make it approximately equals to 0, this green line would try to tilt, and it would and at a time it would become the tangent at this point. Because see, when you decrease h, the slope of this line is changing, and the slope would change and change until it becomes the tangent at this point. So until the green line PQ becomes the new green line I have sketched, we would be decreasing the value of h. So this thing would only happen, this green line would only behave like this when h becomes approximately equals to 0, or we can say when h approaches to 0. So we wrote the definition of derivative as the limit when h tends to 0 for f of x plus h minus f of x divided by h. Now what we are going to do is, instead of doing this in terms of f of x, we are going to define a new equation instead of f of x. So we would be writing, let f of x be x to the power n, and the formula for finding the derivative was limit h approaches to 0 f of x plus h minus f of x divided by h. So we need f of x, which we have over here. We also need f of x plus h. So if f of x is equals to x to the power n, then what would be f of x plus h? Simply, if this is like this, if this is something like this, then if I put x plus h inside, then this would also be x plus h. So we can say that f of x plus h is equals to x plus h to the power n. So now we can substitute these values into this equation. So we can say that the derivative is limit as h tends to 0 for f of x plus, instead of writing f of x plus h, now I will be writing x plus h to the power n minus x to the power n divided by h. Now this is what we are going to focus on now. So our target is to simplify this and turn this into a beautiful and a simple formula which we can use in our regular calculations. Instead of doing all this f of x plus h over and over again, we would try to resolve this and create a simple formula that you will be introduced mostly at your school. Like whenever you're going to start doing derivatives or doing differentiation, you would be introduced to this formula directly. But I'm trying to give you the understanding, trying to make you understand that where did it come from. All right, so let's just try to do this expansion. So if we expand x plus h to the power n, we can write this as x to the power n plus nc1 x to the power n minus 1 times h to the power 1, which is h, right? And then we're going to add nc2 and x to the power n minus 2 and then h squared. Similarly, we can continue and we can go on like this. We can say nc3 x to the power n minus 3, then we can say h cubed, and this would continue forever till it reaches h to the power n, right? And remember, we have x to the power n subtracted at the end, so we will also subtract that x to the power n from here. So this part is basically the expansion of this, and this x to the power n is this x to the power n. Alright, now we have h divided at the denominator, so we're gonna write the h over here, and of course we have to take the limit, because without the limit this expression would simply be the gradient of the line PQ, not the tangent. So we have to say limit as h approaches to 0. Now what you can see is that this x to the power n can be cancelled out just like that, because this minus this would be cancelled out. So you are remained with nc1, which is n, then you have x to the power n minus 1 times h plus nc2 times x to the power n minus 2 times h squared plus nc3 times x to the power n minus 3 times h cubed, and at the end you have h to the power n divided by h, right? And of course you have to give the limit again, because this is the most essential part. And as you can see, all the terms over here have a h multiplied with them, right? You have h over here, you have a h over here, you have a h over here, so all these terms have a h multiplied. So what we can do is we can take h as a common number, right? We can say h, then we can write n x to the power n minus 1 plus nc2 times x to the power n minus 2 times h. Remember, we are taking one h common, so instead of h squared it will be just one h, and then nc3 times x to the power n minus 3 times h squared. The 3 will reduce to 2 because we have taken one h as common, and the last term would be also one thing, I didn't put the dot sign over here, but basically there are more terms in between this, I just didn't show them. And at the end you have h to the power n minus 1, because you had taken one h as common, so instead of n it would be n minus 1. And then you have the denominator h, so you will just put there. And as you can see, we have h over here and we have h over here. We can simply cancel this h from the numerator and the denominator, and we will be remained with n x to the power n minus 1 plus nc2 x to the power n minus 2 times h plus x to the power n minus 3 times h squared, and you're going to continue till h to the power n minus 1. And of course you have to give the limit, which is h tends to 0. Now see, all these terms except for this first term, all the terms over here, this term, and all the terms in between till the last term have one h with them multiplied, right? So as you have just removed the h from the denominator, now you can simply plug in this h approximately equals to 0 in the expression, and it wouldn't make any difference because we have removed the restriction that we had. Because remember, we just said that limit occurs when we have a restriction in the function, when the function is undefined at a certain point, but we have just simply removed it. We are not considering the fact, we are not considering the point when h was 0. So we had cancelled this, so it removes our probability, or it removes our chance that h would be divided by, the denominator would be 0. So we have this expression as is, right? So now we can directly put h into the expression, and as we are saying that h is approximately equals to 0, we can simply say that we can simply plug in h equals to 0 in the expression. So the expression would be n x to the power n minus 1 plus nc2 x to the power n minus 2 times 0 plus x to the power n minus 3 times 0 squared, plus all the terms would have an h multiplied with them. So basically all the terms would have a 0 multiplied with them, and anything multiplied by 0 is 0. So you don't need to write all those things, right? So, and the last term would be 0 to the power n minus 1. And this is also 0. So this thing would evaluate to 0. This thing would evaluate to 0. And all these terms over here would certainly become 0. So you are remained with this part only. You are remained with only n x to the power n minus 1. Now, this is what we call the formula, the first formula for differentiation, and this is normally known as the power rule. Alright, we will expand on this further, but it is important that you understand where did it come from. What we did was we started from the first principle of differentiation, or the first principle of derivative that we had discussed previously, and we replaced f of x with x to the power n, and then we built up on the formula, we expanded using binomial expansion, and then we simplified, we took some h common, we cancelled out the h from the top and the bottom, and we have been simplified to this form. And from here we had just plugged h equals to 0 in the expression, and we have finally reached to the power rule, right? We have finally reached to the power rule. Now in the next class we're going to see how we can use this power rule in different examples, but for today this was my goal, to show you where this formula comes from.